Great. Well, thanks very much, Stuart, for the introduction, and thanks very much for having me here to speak today. So I'm going to be talking about a project we've had going on at Disney Research for the last few years in automated sports broadcasting. And really, the simple way to think about it is that, for a real broadcast, you roll in a big truck like that, and a truck of that size will not fit at Carnegie Mellon University, which is where our lab is. And so we kind of thought, how can we make it look like ESPN came to CMU? Let's use computer vision, let's use machine learning, let's use robotics, make it look like a big truck came in and did a full ESPN production in a much smaller market, in a much smaller venue. So that's the whole idea behind automated broadcasting. The way I think about it is that we essentially have to detect and track the players. We need to learn what's going on in the game. Once we know that, then we need to anticipate and plan to be able to figure out where do we point the cameras. And then once we're able to solve that problem, then the final thing is, of course, we've got robotic cameras. We need to make sure that those robotic cameras are pointing where we want them to point. And then even then, once we can get cameras covering the action, there's still the whole other side of broadcasting, which is cutting between the cameras and being able to tell the story of what's going on in a game. So we're going to cover most of that in the talk today. I'm going to start off just by focusing on essentially the detection and the tracking problem. So our approach has been to use computer vision for a lot of this. I think the other obvious way to be tracking players is to put RFID tags on them. For a variety of reasons, we've decided to go with camera-based systems, mainly so it's completely unintrusive. So the first step, of course, is to find a place and set up with cameras. So in this setup here, we're on a field hockey pitch, and we have 8 machine vision cameras, which have been placed pretty high up towards the top of the lighting poles around the field. And we have 8 cameras, and each camera is giving you a view that looks something like that. So they're looking further straight down. And generally, we can cover the field with 4 cameras. But because we lose a lot of resolution going across the field, we've got a second sort of complementary camera on the other side. So you can think about this as 4 pairs of cameras looking at each other from either side of the field. There we go. So this is the sort of input that we're getting from the camera. And so now the main step here is let's figure out where the players are, figure out who the players are, and then ideally, too, what they're going to be doing as well. So anybody who's worked in computer vision, one of the standard things that we do is just run background subtraction. It's a really easy way to throw out a lot of the pixels that we don't think are important for understanding what's going on. I'm going to zoom in here, and you'll see sort of what the problems are. So in this case, we've got a whole bunch of blobs, and what we'd like to do is tell the computer this blob is player 1, this blob is player 2. The main problem with background subtraction is that in one case, we have a player who got picked up with the lines on the field as well. And so when we go to do blob analysis and to try to find that player, the computer's not going to see that because that player is essentially attached to the field. And so when we're looking for blobs of pixels that roughly approximate the shape of a human, it's going to skip over that person, simply because that line is attached to it and it's not going to see it. In the other case, we've got a player who actually got segmented completely, so the torso is separated from the legs. And so you have to start doing all this reasoning to say that if I have blobs that are nearby, maybe one's like part of a player, maybe a nearby blob is another part of a player, you got to start sort of figuring out what combinations can I fuse together to create what would constitute a single player. And so for a variety of reasons, that's why we don't do this. This has sort of been a standard way in computer vision to do it. And you might be able to get there, but it just seems that there's so many combinations and corner cases that you have to worry about. So instead, our approach is to take the camera like this, and we're going to calibrate it, which means once we know the geometry relationship, we can take that camera image and we can map it back down onto the field. And when you look at this projection from the top-down viewpoint, it's skewing everything. So what that means is that the player's feet are actually in the right location on the ground plane here, but then the rest of them kind of gets splattered onto the ground like a shadow. So where the head appears on the ground really has nothing to do with where the player is actually located. So let's look at this another way. So here we have our camera. There's a green blob on that camera representing something we picked up. We've got a player standing on the ground, and we can then do that projection. So we can take something from the camera image and we can lay it down onto the ground. So as I said, the feet end up being in the right spot, but then the rest of the player kind of appears like this purple shadow. And so our real insight was that we don't have to project just on the ground. We can equally as well project to planes above the ground. And so sort of as you scrape through, you can go to a plane that's roughly the height of a person standing upright. And when you project to that plane above the ground, the head's now going to be in the right place, and the feet kind of get cast in front of them. And so we can repeat this for any number of planes in between. as well. And so when we integrate vertically, we basically get this sort of triangle response of the player's profile. And so what really we're going to be doing, the nice thing, I suppose, is that the apex of this triangle lines up exactly with where the player is actually located in the world. And so what this is going to boil down to is, let's take an image like this. This one's particularly challenging because we've got strong lighting conditions, and so lots of shadows are being cast on the ground. So again, when we do background subtraction, the players come through, but all the shadows come through as well. And so what we're going to do now is take this image, and instead of projecting it just on the ground plane, we're going to project it on a whole bunch of planes on the ground as well as going above the ground. And so when we do that, you can kind of see this is where the players are, the shadows are coming through, but they're all kind of blurry. And so the idea now is to say, aha, I know I'm looking for this triangle response. That's indicative of a player standing upright on the field. So what we're going to do is zoom in, and remember that's sort of the model that we're looking for. And so along this cross-section, which lines up with where the camera was located, we can sample the image at a particular location, and we can make sure that those samples match up with the sort of triangle response we're expecting to see. So this essentially is basically template similarity. We know what we're looking for, and let's test each location in the image to see if the image evidence supports the sort of, or justifies a player standing there. And so coming back to the sort of the big example, that's the original input that we got from doing background subtraction. We can then filter it, and for the most part, all the shadows and everything else disappears. We kind of just get these blobs, regions of where we think players are standing. And so the last step is we run mean shift, and that gives us the player locations of where they are on the actual soccer field, or field hockey field in this case. So the nice thing about the method is that here's the camera image. We compute the occupancy map. That is, for the most part, completely done on a GPU, so it comes up pretty much instantaneously. Ideally, if we had all the time in the world, we'd run a Richardson-Lucy deconvolution, which is essentially what I proposed to do template similarity. But instead, in our method, we can do it in 30 milliseconds on the GPU. So in our approximations, pretty close. As long as players aren't right on top of each other, we're able to find players on the field. So let's see, is that running? Hopefully you can see it. So these are the players running around, and this is the sort of live real-time player detection results that we can get on it with 1 frame latency from the GPU. So for the most part, it'll be right on top of the players. When they cross over, we'll lose them on occasion, but we don't get confused by a lot of other things that could be coming through in the image. The nice thing about the method, too, is it works really well in rain. So all the raindrops pouring down would drive any computer vision algorithm crazy if you're doing everything on the image plane. But the fact that we're doing this in sort of 3D geometry, reasoning about what's going on in the world, and the camera projections, for the most part, we don't get confused by the raindrops at all. Similarly, because these cameras are about 18 meters up in the air, those poles are designed to flex with the force of the wind, so we have to deal with a shaking camera as well. And so again, for the most part, the sort of the swaying motion that we get in the camera wrecks background subtraction, but for the most part, we can see through that, and we can still find the players. And then the last sort of big case that you have to deal with outside is these strong shadows. So we do pick up the shadows occasionally. That's mainly the problem of when a shadow lines up with the vertical vanishing point of the camera, it's hard to tell the difference between the background subtraction result of a player and the background subtraction result of a shadow. So there are a few corner cases that we have to worry about, but generally, even in all these sort of really harsh imaging conditions, being able to reason in this way gives us real-time detection results that are quite reliable. And so as I said, we have 8 cameras set up in field hockey. So this is what we can get from a single camera, but then we have 8 cameras running simultaneously. And so you can see that each machine essentially processes 1 camera. We're getting all these independent detections. We can then project those onto the field hockey pitch, and we can then also look to say that if I see a player in 1 camera and I should be able to see them in another camera, let's look for that supporting detection. So that's another way that we can then filter out these corner cases where shadows might come through in 1 camera, but given the vantage point of the other camera, the shadows aren't going to get detected. And so we can quickly start to filter out by looking sort of for reinforced detection results of the same player from different perspectives. And so then moving indoors, we've got this set up at CMU. So in this case, the basketball court's a lot smaller. We can cover it with just 2 cameras, which are placed up at the ceiling. And then because we're doing remote broadcasts as well, we have 3 robotic cameras that we can control as well. The great thing about this algorithm is that we tuned it originally outside on field hockey. We dragged everything indoors. We didn't touch a thing. And we were finding basketball players pretty much immediately. The only change we had to do was tell the computer we're looking at a basketball court, and not a field hockey pitch. And so once you account for that change in geometry, the algorithms, for the most part, find all the players. And as you can see, too, we run in real time with 1 frame latency to get player positions. I should point out the latency is absolutely critical for what we want to do when we're driving cameras. And that is that the longer it takes for us to find out what's going on the field or on the basketball court, that delay will then kill us later on when we're trying to tell a camera where to look. So we need algorithms that essentially run with no latency whatsoever. All right. So moving on, we kind of talked a bit about detection. I've skipped over tracking. I'm happy to talk about that afterwards if people want to. And then I'd like to focus instead now on the anticipation and the camera planning problem. Now, first we thought this would really be quite straightforward, and that is simply follow the bouncing ball. I think that's sort of the basic rule of camera control for sports. And so if you think about what that actually does, here's an example. In this case, there's an RFID tag. We're not following the ball, but we're going to follow the player. And so this player is moving back and forth to play tennis against the opponent. And then I guess the one sort of obvious thing from this is that that camera doesn't look like it's controlled by a human. It's pretty obvious that if a human were behind the camera, they would be doing a much better job of predicting where the player is going and framing the shots to show you what's actually going on. And so following the bouncing ball is a nice way to think about this problem, but I don't think it actually describes the real thing that we need to do from an algorithmic point of view. Fortunately, the other way of looking about this, or the other quote from this, is that anticipation is really the key to composing shots for sports. So let me explain a little bit of why camera operators need to anticipate. So in this case, we're looking at field hockey. We've got this player here has the ball. Is it going? Oops. Let's go back. That player there on the top left has the ball. And so the camera has framed it. Is this video going to play? There we go. That player's got the ball. And so the camera's framed it, essentially putting that player on the 1/3 line. And 2/3 of the image are reserved for where we think the action's going to go. Now, as soon as there's a turnover, the camera's going to reframe that shot the other way. So the ball now goes on the 3rd line on the opposite side of the image to show you essentially this is where we expect the action to go next, right? So the camera operator is taking into account not only where's the ball right now, but potentially what could happen next? Who are the teammates that are there to receive a pass? Where's the opposition going? They're trying to take away space. And so the camera operator is reasoning about all of those things simultaneously and then trying to express that in terms of their framing and their composition of the shot. Now, the argument that camera operators anticipate is that they will also make mistakes. They will misinterpret what's going on in the play. So in this hockey example here, this player's got the puck, and he's going to get pressure from the opposition coming in, as well as this white player, defense player, is going to be taking away a passing option. And so this player essentially has two options. He can pass to his teammate across the ice, and he can pass to another teammate, which you don't actually see in the view here. And so you can watch what the camera operator does, expects one thing, realizes that they're filming a bunch of players sort of skating around on the ice without the puck, and then panics, but fortunately manages to find which player actually has the puck again. So there's sort of, I guess, 2 takeaway things from this. The first one is obviously they have to anticipate, and when they make mistakes, they need to recover from it. The really interesting thing about how they recover is that the camera was still moving smoothly. Even though the camera operator kind of realized they'd made a mistake, and they're then figuring out what's the appropriate framing to do, that footage of the camera operator searching did not look at all like the robotic footage of the tennis player. And so that tells us as well that there's a whole bunch going on in terms of how you move the camera that's absolutely critical. And so to do that, we basically decided let's avoid all the rule-based systems which might work for doing camera control, and instead let's learn and let's try to mimic what human operators do, because they're obviously doing a whole bunch of reasoning in terms of where they're pointing the camera. So in this case, we've set up at Wide World of Sports, which is one of the complexes at Walt Disney World in Florida. And I'm just going to step back before we get into sort of the learning algorithms to realize what's going on. We actually have 2 cameras set up. So the first camera is up top on the ceiling. That's the one doing the player tracking. And so that's going to be spitting out essentially player locations. It can also do team classification. And so the representation in terms of what the computer's seeing in the game is that basketball court with a whole bunch of dots on it. So as far as the computer is concerned, that's its understanding of the game. The input of what we'd like to do is then the human camera operator. So we have operators there that are filming the game. And so much like we had to run computer vision to be able to extract player positions from our player tracking cameras, we also have to use computer vision on the broadcast camera to go backwards and figure out what essentially was the pan, the tilt, and the zoom at each shot, or at each frame in that broadcast view. And so then once we've got those two things, that then becomes our learning problem. So essentially we have a whole bunch of features going in, and we've got a whole bunch of labels from these human-generated broadcasts. And we want to figure out what's the mapping between the feature context coming in and the ultimate camera output that the human gave us. So we've cast this as essentially a learning from demonstration problem. So we take the human footage that we've got. You can see the court markings have been superimposed on top. So that's the output of our algorithm to essentially calibrate the camera at every video frame. So we know the pan, tilt, and zoom of the camera. And then we've taken our player tracking results, superimposed them there as well to show you that, indeed we do have a camera that's calibrated and we can jump between those two perspectives of the two cameras. And so what we'd like to do is learn some kind of structured regressor which can take the examples from the human, take the player tracking data, and then output a pan, tilt, and zoom at any given frame, ideally with, again, zero latency, so that we can then tell a robotic camera, this is how I think you should be, composing your shots based on what we've seen in our training data. So the baseline approach is essentially we're going to record lots and lots of basketball of both the player tracking data and the human camera operator, and those are going to become a whole bunch of example sequences of what we should be doing with the camera. Then we can take a sliding window and we can scrub through that data, and at each sort of window location, we're essentially extracting this is where the camera should look right now based off what the human operator's done, and the context is where players have been previously as well as where they are right now. And then at that point, you could feed that into any black box predictor you want. So we've done a lot with either just linear regression, random forest regression, support vector regression. If you had enough data, you could easily be doing some sort of deep learning on this as well. And so the idea there is essentially, where should the camera be looking right now? And you just make that sort of prediction. The problem is that it's not always obvious exactly where the camera should go. There can sort of be multimodal options for a camera operator to pick. And so when you're generating this output, it's going to be very jittery from one frame to the next. And so you normally want to then incorporate some kind of temporal consistency so that you can send this off to a robotic camera and not, otherwise you'd be sort of frying the motors on your robotic camera, asking it to look here and then instantaneously look somewhere else. So you need to have a nice smooth signal that you can send into the robot. So one obvious way to do that is just take a causal filter. So again, in our case, I guess the baseline would really be some sort of linear autoregressor to say, given previous camera positions, this is how I expect the camera to be constrained by sort of the physics of how it can move. And we use that to then smooth everything. And then as a result, we can generate the predicted camera sequence. So I said the main problem is that the black box predictor is going to be noisy. It's also going to be multimodal in a lot of cases. And so as a result, you've got to tune your smoothing filter without the context of what was going on originally. So a lot of this will be take a noisy signal, then with your common filter, you've got to go through, estimate all the parameters that you think. You're trying to tune that thing, and that becomes now a separate learning problem that you kind of have to have a whole additional held out test data set to be, now that I have my sort of rough predictions of where the camera should look at any given time instant, let's go through and estimate all these filter parameters and try and get the appropriate clean signal out of it. And the problem, though, is that the filter doesn't get the contextual information of player data. All it gets is a noisy prediction of where the camera should be looking right now. So our approach has been to turn this problem completely around. So we actually want to take that causal filter, and we want to inject it back into our black box model. And so basically, it's sort of saying that I know the signal needs to be smooth, so let's change the machine learning and not just learn any kind of signal, but let's learn signals that will always generalize to generating temporally smooth signals. So essentially, we get rid of our black box predictor, and we're going to call it a one-step predictor. And instead of focusing primarily just on accuracy, this one-step predictor is going to focus on accuracy as well as smoothness simultaneously, where the concepts of smoothness are essentially being injected in by this causal filter. And now, because we just have a one-step predictor, in practice, we can roll that out. And so that one-step predictor is going to be generating the entire predicted sequence for the camera. Now, of course, when the training data comes in, we still need to learn what is smooth, right? In particular problems, the filters are going to change from one domain to another domain. So we can take the training data coming in. We can essentially learn what are the filter coefficients that describe the smoothness characteristics of the sort of training ground truth signal that I'm trying to learn. once we have an idea of how to describe smoothness using that filter, we can then inject it into our one-step predictor, and then we can generate our predicted sequence. In practice, what we end up doing is then iteratively retraining. And I'll come back to that in a second as to why we're actually doing that. But generally speaking, it's that you're not going to be able to get this right on the first try, and we need to get a robust system that can actually learn from the mistakes that it's making. The way I like to think about our approach is essentially data-driven approaches to learn Newton's equations is an inefficient use of your data. Newton came up with the equations of motions a long time ago, and what we need to be able to do is take that prior knowledge and somehow shoehorn that into a machine learning approach so that we can use all of our data to learn where the camera should be looking and not the fact that F equals ma. It's just an inefficient use of your data. The other way I like to think about our approach is that it's analogous to learning how to ride a bike. And so from our training data, we have a human camera operator who always showed us exactly what to do at any given time instant. The way you can think about that is that that's the parent holding onto the bike. And so at any given time instance, the child's trying to learn, where should I be pointing the handlebars right now to keep the bike upright and not fall over? And so in our training data, we've always started with, here was the previous sort of ground truth camera operator control, and then it's like the camera operator let go of the camera for that instant, and the machine learning algorithm has to take over, and it's got to try to predict where should the camera look next. And so when you use all that training data, we've never seen a situation where the bike wobbled, simply because we were under constant supervision. And so the algorithm that we're proposing is essentially like loosening that grip on the bicycle. So we start with a really, really tight grip. We learn exactly from the human operator. And then in the next iteration, we're going to release that grip ever so slightly. And that's going to essentially allow the bike to wobble. And the child's going to be able to experience conditions that weren't identical to the training data. So you start to realize the bike's getting unstable. How do I control the steering wheel to get the bike back into a stable position? The analogy I suppose the baseline approach is we train by holding onto the bike, and then I'm going to let go, and I hope you can figure out how to recover from an unstable situation you've never seen before. So just, I guess, to step back a bit, here's the problem that we're looking at. So in time, we've got plotted along the x-axis. Y is then essentially theta. That's the angle that we want the camera to be looking at. Given in time, I've got x representing all the feature data that we could pull out. So again, that's the dots on the basketball court that are colored, essentially telling us where the players are. So we can get a sampling of where the players are at time 4, time 3, time 2, and time 1. And what we'd like to be able to do is have some function that will then predict where that robotic camera needs to look. Now, as I said, we've got this demonstration from the human camera operator as well. And so we can just step through how do we take our sliding window and generate all of these training examples. So let's look at time 4. Essentially, right there, the ground truth position where the camera operator looked is our target label. The features coming through underneath, unfortunately, you can't see this, are x4 and x3. And then there's the blue dot shows you the previous location of the camera. So in this case, we're essentially training on a window that looks back one frame. So we're trying to say, given the current player positions, as well as the player positions at the previous time, so in this case, time features x3 and x4, as well as where the camera was looking previously, which is that blue dot, we're trying to predict that yellow dot, and that is where should the camera be looking at the current time instant. And so we can sample these sort of one-step, one-window examples from the entire sequence, and with all of those training examples, we can then come up with some function, y of t, which is going to take the current player position, the previous player positions, as well as the previous camera angle, and it's going to predict where the camera should be looking right now. And so that's just a standard supervised learning approach. And you can always go back and basically apply it to your training data. So we can roll out that one-step predictor that we learned and see what it actually did on the training data. Now, maybe if you're lucky, you can reconstruct the training data perfectly, but in many cases, you're always going to have some sort of residual error on your training data. So just for reference, this is the ground truth of what the camera operator actually did, right? So we've got some discrepancies in our training data already that we weren't able to capture it exactly. So if we return to that same example of let's look at time 4, the target's still the same. We still always want to be looking at where the demonstrator told us the camera should be pointed. And the feature data is still the same. We still have, this is what the players were doing at time step 4. Previously, this is what the players were doing at time step 3. The main difference now is that the previous camera position is not the ground truth position, but the previous step in our rollout of the predictor that we had just learned. And so this is where that wobbling comes into play, right? Up until now, the previous training example we had was right on the right path, and all we had to do was predict the next ground truth step. In this case, we've essentially wobbled off what we should have been doing according to the human demonstrator. And so this is a situation that we don't actually have in our training data. So even by rolling out on the training data, we're essentially looking at how the algorithm's able to generalize to situations it's never seen before, simply because we're starting to propagate errors that we make at earlier time instances, carrying them forwards, and then throwing us into a new state space or a new state example that we've never seen before. So if we write this out and think of this as a training example, what we're basically telling the learning algorithm is that you drifted off at time 3. Here's the necessary correction you need to make to get back on track at the current predicted time at time 4. The main problem here is that that might not be physically possible given our smoothness constraints, right? Is that we could simply do this, but then we might be violating all of the sort of conditions that we can't deviate too much from the current trajectory or the current sort of instantaneous velocity that we have on the camera. And so our insight was, let's not tell the camera to do a drastic correction, but let's instead do a sort of a more subtle correction. So let's come up with a new target, which I'm showing here in green, which is essentially trying to push the learning algorithm back to where the ground truth is, but doing it in such a way that we're not violating the smoothness constraints. So we can look at our smoothness model and figure out what's the sort of maximum allowable change that we think we can induce into the current situation to get us towards where we should be looking. And so we basically come up and hallucinate all these new targets. And so you can think about this as we start to wobble on the bicycle, instead of instantaneously trying to get right back perfectly, let's at least get back to a more stable situation. And so yes, I guess the ultimate step there, unfortunately you can't see it, is that we change from our ground truth target when we're training to this hallucinated target. And so then we just iteratively do this algorithm over and over and over again until we converge. So we start with very, very conservative smoothing conditions, and then we essentially re-estimate our smoothing filter each time, and we're able to converge to a good representation of what the human actually did, in this case, after about 10 iterations. So the blue curve is the ground truth, the red curve is the output of our learning algorithm at each of the iterations that are shown underneath. And so here's a side-by-side comparison, essentially between what I propose as the baseline. So that would be taking a support vector, a random forest regression rather, running that through a common filter. And then the main problem too, is that you induce a delay when you're doing all of that as well. So we have to make predictions, but by the time we're actually able to sort of smooth everything out, partially looking into future observations, we induce a half-second delay to get that kind of camera control. And you can see that it's really quite uncertain where the camera should be looking at times. It's hesitating, it's jittering, and so forth. On the right-hand side is essentially our recurrent predictions that we've trained with this model. And so we're able to get rid of a lot of the high-frequency jitter that you see in the camera control. And it's essentially, it's learning that given the current game situation, this is when you actually should be moving the camera versus trying to be much more aggressive about getting perfect framing. All right. And so, of course, we ran a user study on all of this as well. We compared against a whole bunch of baselines. So the one I showed you there was probably the most straightforward you can do, where you just do a random forest regressor or any kind of supervised learning you want to predict instantaneously where should the camera be looking, and then smoothing that. In this case, I guess we used a Savitsky-Golay filter. We tried common filters. We also tried dual common filters, which are essentially one's trying to learn the coefficients of the filter, and the other one is doing the actual sort of standard common filtering. And then we looked against some filter forests and conditional random forests as well. And in all cases, according to the user studies that we ran, we really did have something statistically better. The disappointing thing is that when we run against the human baseline, it's still inherently obvious that the human's doing a much better job at controlling the camera than we are with our learning algorithms. So I think it's safe to say that we've got an algorithm which seems to be doing better than all of the sort of other automated ways we can do this right now, but we still haven't passed the Turing test in terms of can we get something and generate footage that looks indistinguishable to what a human operator is actually doing. So unfortunately, that problem's not yet solved. And so stepping back, this is what's going on, or this is the broadcast room at ESPN Wide World of Sports, and you can see this is about as small as you can get to still have a professional production. So they normally do a 6-camera shoot. All those video streams come back to the production studio. They've got the producer up front who's calling which cameras are going to air. They've got other people to switch it. They have the commentators just offside in another audio booth. They have stats and everything else going on in here. They have replay operators and all those kinds of things. And so that's all working together in this, they kind of learn each other's mannerisms and what they're going to do for a broadcast, and so they can just kind of work as a team in unison without actually having to explicitly tell everybody what to do. And when they work together, this is the sort of broadcast that they can output. So you get a really good game camera, which I said, I think we're getting towards doing something sort of approximately reasonable for that. But then they can switch to other cameras like this, and they can also figure out the storytelling aspects of when do you cut to the coach, when do you cut to players high-fiving, and so forth. And that's, to me, the whole next step that we need to do in automated broadcasting. We've been able to talk a lot today, at least about how we're able to detect all the players, how we're able to track them to some degree. We've talked a lot about anticipating and planning to drive the game camera, but I think there's a whole other side of how do you anticipate and plan to drive the auxiliary cameras. So which players should you be focusing on to get close-ups? And even then, once you've solved the camera, you can plan and get each camera to look where you want it to look. Ultimately, you still have to come down to decide which camera goes to air, and how do you cut between cameras to tell sort of the emotional arc that's going on in a story. So when do you cut to a coach? When do you cut to a player getting a high five from his teammates? All those kinds of things. So that's still very much the open research problems that we're looking at Disney Research. And with that, I'd like to thank you very much for your time and attention, and I would be happy to answer any questions you might have. Thank you.
Thanks very much, Peter. Peter, perhaps when you have the question, you could repeat it for the microphone.
Did you personally install those 18-meter cameras on the field hockey field?
Yes. Yes, I did. So the question is, did I install all those cameras? Yes, I did. I think every camera setup we showed, I have put those cameras in place. So you get to do all the algorithms, and then you also get to go into Boom Crane. And in some cases, you do it at 3 in the morning, because that's the only time the facilities are closed to give you access.
Some more questions? Pat, I'll pass you the mic.
So Pete, you mentioned, we're still a long way from replicating what a human can do. Do you think that's just a function of data? So how much data have you actually used for your prediction algorithms? Just a couple of games, or do you need thousands and thousands of games to even think about replicating an expert?
Sure. So the question is essentially, how much do we have enough data? To achieve human performance, is it a matter of just collecting more data, or do we have to go back and get new algorithms? So the data that we did train off was essentially 2 games at Wide World of Sports. The main challenge that we found, though, is that we've got data from both CMU as well as Wide World of Sports. CMU is Division III college basketball. Wide World of Sports was high school all-stars. And so, we had done a whole bunch of training on CMU data, brought that down to Orlando, hit go, and then realized that as far as the computer was concerned, these were 2 different sports that were being played. Is that you've got, when you walked in, there was a sign that said, NCAA scouts, you sit over here. And so, we had all these high school all-stars showing off for the scouts as to how good they are and give me the college scholarship. Whereas Carnegie Mellon tends to be much more of a systematic team play, use the shot clock, get your shooter in the right place at the right time. And so that's where we saw this complete, disparity between, I'd say, the distribution of samples we have at CMU and the distribution of samples that we have there. I think, we got reasonable results from 2 games. Having 10 games, having 100 games, or having 1,000 games would make me much more confident that we're doing something reasonably well.
Thanks. That's awesome. Are you working on automating commentary too?
So the question is, are we doing automated commentary? We have looked at that in the past. It's not something I'm actively looking at right now. I think, the general problem is detect what's going on on the sports surface, wherever that might be, and then try to understand what's going on, and how do you even show that you're understanding that? So I think one way is you could generate a commentary to see, this is sort of the natural language that we're generating from it. I think pointing a camera is probably the most or I guess the easiest way to show that you're understanding. It's like, this is the thing I think that we should be focusing on. So for me, that seemed like the easiest way to just have these algorithms, run them, and say, okay, we're actually learning something here, and it seems to understand what's going on. I think then the next step is, yeah, if you could generate commentary to describe exactly what's going on. It becomes really difficult, because right now, all we have are just a bunch of dots moving around. So I think when I look at these things and I try to debug what's going on, the very first thing you do is actually just turn off all the video. And all you do is just look at a whole bunch of dots moving around and say, can I understand what's going on? So you look at it and you sort of, it's like, we don't even track the ball. But there's a good intuition of which player has the ball. And so you can kind of look at these dots moving around and say, yeah, the ball's somewhere over here. And so, yeah, I think that's just, you can trick yourself if you look at the raw data that we capture and then realize we're running computer vision to extract all the data out of that. And so you might think, oh, yeah, pose of players. You can see that in the video, but right now our computer systems can't. So I think you have to keep all that in mind when you're trying to figure out what are we actually understanding.
Have you tried applying it to other sports, the algorithm, like hockey or soccer? And if so, how did it perform?
Sure. So the question is, did we apply it to other sports? Yeah, we've applied this to soccer. It works reasonably well, not nearly as good. And I think there's two aspects to that. The first one is that the soccer camera we have is actually a remote camera, so it's controlled by an operator in a room with a joystick. And so you don't get the same sort of fluid motion that you have from a camera operator right there on site using a fluid head tripod. So I think there's a bit of a disconnect between here's the example data that we're getting of where the camera should look versus what the signal would look like if we had a real camera setup and a real operator there. I think the second problem is that soccer players tend to hold their formation much more than basketball, and so the fact that we're not tracking the ball makes it much more ambiguous in soccer as to where you should be looking to follow the play. That tends to be not quite a completely rigid formation that moves up and down the field, but it seems to be less apparent where the ball is given soccer player data than it is from given basketball player data.
I have a question over here. Somebody put their hand up. No?
Do you have access to all 6 cameras, continuous feeds, and then like treat which camera was cut to as kind of a label, and maybe do some kind of reinforcement learning, or I'm thinking like DeepMind, except for choosing which camera to cut to realistically and over time. Has anybody tried that, or is that something?
Yeah, so the question is, do we have access to all the camera feeds? And yeah, what are we doing in terms of reinforcement learning and sort of other things that we could be doing? Yeah, we do have access to all the camera feeds. So we are able to see this is what the auxiliary cameras are doing. The other really neat thing is that we also have the audio chatter of the production group. So there are times where the director will say, camera 4, get me a shot of this player. And so you can kind of get even the direct supervision if we somehow figure out how to encode all of that as a feature and manually annotate it. I should say that the algorithm that we're using to essentially mimic the human camera operator is really simple to Dagger or dataset aggregation. So we've been looking a lot at reinforcement learning algorithms and trying to figure out how can we adapt those specifically to the domains that we're looking at. But yeah, I think the general idea of reinforcement learning seems to be perfect for what's going on here. And that's what we'd like to do in the future, right, is that you've got this whole corpus of data, you see how well we're doing right now, you'd like to go into active learning and just deploy the system and say, no, you screwed up the camera shot there, much like going through film school. And how do you make sure that as we start to give new training data, we don't then screw up things that we were doing well before?
So have you ever thought about incorporating like video game data into your training set? So where the soccer players would be positioned on the field and where the camera would be pointing in that specific situation for a video game, because where everybody would be already, incorporating that as training data for where to point the camera in real life.
Right, so this is, what can we incorporate essentially synthetic data from video games as a way of inputting it? Yeah, that's definitely something we've thought of. There's 2 ways to go about it. One is you simply just steal the video feed being generated by the game, which means you still have to go backwards. You have to then figure out, this is the calibration of the camera that I'm looking at. So you still have to solve the computer vision problems. Ideally, what we'd love to be able to do is to dig into the game engines themselves and simply get the much more like the direct feature representation to say, these are where the players are on the field, this is where the camera's looking, and then not look at the images at all and work down to that level. Yeah, I think if we could do that, that would definitely be a data source that I'd like to look at.
Okay, I think we have time for one more quick question.
At what point do you think you need to track the ball? For example, say a half-court shot and you want to trigger a replay. Just looking at the player positions on the court, I don't think you'll ever be able to make that call that a replay should be played just based off where the people are, not the ball.
Yeah, there's a whole bunch I would love to be able to do with tracking the ball. So I think for the game camera, you can get away with it. As soon as you even want to figure out, if it was a successful shot, and I want to cut to the player because maybe they're high-fiving with their teammates. Yeah, you kind of have to track the ball to go backwards to figure out which player actually took the shot. So you can either say, like, fine, we'll just solve it by doing pose recognition. But if you had the ball, you can do it. The other thing right now is that we're not even incorporating the scoreboard. We can tap into the scoreboard. We can get contextual information like the clock and the score and so forth. But that then requires, like, we still need a human there to run the score clock and everything else. So if we could do all of that from a vision point of view as well, then it's sort of completely automated, and you can do it for your pickup games and so forth, right? So yeah, I think the more data coming in, the better, but we have to come up with smart ways to do it where we're not dependent on humans always to be there to input some of it.
Okay, great. Thanks very much. Peter will be here for the morning break, so you'll be able to ask some additional questions of him then. I'm sure he'll be available. But please join me in thanking Pete for a really interesting and intriguing presentation.